Hi, and welcome to this demonstration of the product line product variant co-evolution support tool developed by the University of Hildesheim for Work Package 5. The purpose of this tool is the automated migration of semantically related lines of code that, for example, represent a new functionality, feature or bug fix from the product line into the derived product variants, which we call update scenario, or vice versa, which we call feedback scenario. As an example, consider a product line at an arbitrary point in time, which we call here T0. For a specific customer, we derive a particular product at the same point in time by instantiating the variable code such that only feature A is available in that product. Over time, the product line and the particular product evolve independently, which is a typical scenario in practice. At the new point in time, T1, we introduce a bug fix to the product line and encounter that it is necessary to also introduce this fix as an update into the previously derived product to improve the specific customer situation. In the meantime, we developed a cool new feature for the particular product which we identified as being beneficial for other products too. Hence, we want to feedback this feature into the product line to make it available for the other products. Both scenarios require a semantic unit migration, where the semantic unit is a set of all semantically related lines of code that belong to the bug fix or the cool new feature. As identifying and migrating a semantic unit is a tedious and error-prone task, our co-evolution support aims at automating it. Hence, the first step is to identify semantic units, meaning all semantically related lines of code, for a particular code fragment. This is what we focus on in this video. The actual component realizing the semantic unit identification for product lines and product variants is called Jess. The first step of its process is to parse the source code of the product line or the product variant, which contains the semantic unit of interest, into a code property graph. A code property graph consists of nodes that represent source code elements and edges that represent different relations between them. It provides information about the code structure, represented by an abstract syntax tree, as well as control flow and data flow information. While other tools also provide this information, the unique feature of our tool is that the generated code property graph contains the C preprocessor statements, which are required, for example, to migrate entire features. Hence, it explicitly represents the variability information of a software product line. Based on this code property graph, the next step of the process is to identify the semantic unit with the use of semantic slicing techniques. In order to apply the slicing algorithm, the developer has to define an entry point in the source code for which the slice shall be created. This point marks the point of interest, like the definition of a function or a certain configuration option. Based on the entry point, Jess searches for the respective node in the code property graph and calculates which other nodes are semantically related by traversing the edges. It therefore relies on a set of configurable rules which define which edges are relevant and how to traverse them. The last step of the process is the generation of a foundation for a patch which we can apply to our target, like the product line in the feedback scenario or the product variant in the update scenario. Here, Jess translates the semantically related nodes of the code property graph identified in the previous step into files with the lines of code. These files and code lines follow the same structure as in the source project from which we extracted the semantic unit, but contain only the relevant elements for that particular unit. This patch can then be used to merge the semantic unit into the target product line or product variant. In the remainder of this video, we will show exactly these capabilities of our product line product variant co-evolution support tool. However, we first start with downloading and installing Jess. Then we create the code property graph as the required artifact to identify a particular semantic unit and the generation of a patch foundation using a small and artificial example. Let's start with the hands-on demonstration of our tool. First, we need to download and install Jess. Therefore, we open a terminal and clone the Jess Git repository to our favorite location. By cloning the repository, we ensure that all required components and scripts are available. Further, the repository contains the small example we use in this video to show the capabilities of our tool. After cloning the repository is done, we execute the build script to build all components and receive an executable Jess installation. Note that Jess requires additional software like Java 8 or Python 3, which we installed in advance. The complete installation guide can be found in the documentation of the tool. In order to make Jess work correctly, and as a final installation step, we have to add the local user directory to the path variable. This enables using the Jess scripts from every location. Now it's time to actually use the tool. Therefore, we start the Jess server, which is the processing backend and responsible, for example, for generating the code property graph and creating the semantic units. In a second terminal, we import the project for which we want to create these artifacts. This requires the creation of a tarball package of the source project, which is the actual imported artifact. After the import, we can create the entire code property graph by using a particular Python script. We only need to ensure that we define the correct name of the project in that script. Hence, we define the project name as the name of the tarball package we created and imported before. We save this change to the script and execute it from our second terminal. The result of the script is a new directory which contains the code property graph as a dot file and as a graphical representation. In that graphic, we can manually inspect the structure of the code and its relations as well as the data and control flow, including preprocessor statements. The next step is to create a semantic slice. This process is realized by a different Python script in which we have to check whether the correct project name is defined. This time we do not have to change the name as it is already correct. Further, we have to define the entry point for the slicing algorithm, which we also specified in advance as being a particular feature called analog sender. The slicing algorithm will now produce a slice which contains all semantically related lines of code necessary to migrate that feature. We therefore have to execute the script which traverses the different nodes in our code property graph and select those that are relevant. The result is a directory containing the slice, again as a dot file and as a graphic. Here we see that different start nodes exist as the feature is scattered across different locations in the source project. Further, all relevant lines of code are included. Based on this slide, we can generate the foundation for a patch. Hence, we open the respective Python script and define again the name of our source project such that the script produces the patch foundation on the correct basis. We save this change and execute the script, which produces the third directory containing a subset of the code files of the source project. This set of artifacts will then be used for merging the sliced feature from our example project to a derived one. However, this merging is future work. In summary, we showed you the current state of our product line product variant co-evolution support. More information can be found in the official Jess documentation and on the GitHub websites. Thanks for watching this video.